That post in the middle of the notes was. Yep. Sorry, one.
Okay, good morning. Let's start. So welcome. This is DINRG, so decentralized internet infrastructure. For those who are here for the first time, so DINRG is concerned with like applying distributed computing to decentralizing internet infrastructure services. So a bit of a loose definition. This is Melinda Shore. I'm Dirk Kutscher. And just before we start, the usual IETF IPR policy, which follows the IETF IPR policy. So in short, you have to inform us if you talk about or are aware of any IPR in any contribution to this group. Yeah, we have the usual infrastructure, mailing list, wiki, and so on. The most important thing is that we need a note taker for today, otherwise we can't really do this meeting. And so that means we need a volunteer for that. So usually note-taking captures the discussions after the presentations. Yeah, again, it's really important to have a record of that and enable people to follow what's going on.
Thank you very much.
Thank you. Right. So feel free to use the Etherpad if you like, but you don't have to. So we have an interesting agenda again. So we want to talk. So in previous meetings, the issue came up that well, some of the consensus protocols that we are interested in actually need a reliable and scalable and secure communication infrastructure. So David, Mazie, and colleagues kindly started thinking about this. So we'll talk about that. We'll have a presentation by Christian on the GNU name system. We have Nathan from Singapore joining remotely on Byzantine agreement protocols. And how do I pronounce your name correctly? Brooke is talking about new funding opportunities on next generation internet in the EU that relate to the topics that we work on here. Any comment, any need for bashing the agenda? All right, and let's get into it. And we start with David. And it's a clicker. That would be nice because you're on video.
Okay, thanks. So yeah, so I'm going to start with a little update because for the last N of these meetings, I've been telling you about the Stellar Consensus Protocol and the draft that's in progress on this. And I think the draft has kind of more or less stabilized at this point, at least for the moment. And also, we kind of wrote up a short, like 6-page version. So if anyone has been like, wishing they could understand this protocol better and wishing there were like a simpler description, you could try the simplified description, which I've linked to in the slides here. There's lots of hyperlinks in these slides, which you can get from the materials. But there's kind of what I'd like to do is get this draft to the point there are multiple implementations where we can actually start like baking off one implementation of the consensus protocol against another. But the point is, as we're going now, that's never going to happen. Why? Because the draft doesn't specify what the underlying broadcast layer is, how these messages actually get exchanged. And the reason for that is that there's not really a solution necessarily that's kind of good enough at this point. In particular, there's security issues with most kind of existing approaches to overlays, and the goals for SCP are to provide very strong security, like to be able to send large payments over this thing, or use it for kind of secure software or firmware or certificate transparency logs, or secure IP prefix delegation, things that it might cause a lot of damage if someone messes with it. And so that means that we need some kind of secure underlying multicast layer. And so that's what I'm going to talk about today. It's mostly not my work. It's more like kind of a survey of past things that might be ideas. And, there are no solutions here. It's mostly questions. But if we come out of this and, we gauge that there's kind of interest and requirements, it can like help guide the research. It's obviously like an area that I'm interested in working on. Okay, so let's start with kind of, as a motivating example, the Bitcoin overlay network. I think it's fair to say that the kind of resurgence in interest in decentralized infrastructure is probably at least indirectly due to like the excitement in Bitcoin, just as say like 20 or 15 years ago or 18 years ago is because of peer-to-peer networks and distributed hash tables. So what does Bitcoin do to disseminate messages? Well, a typical Bitcoin node is configured to have 8 outgoing TCP connections and to allow up to 117 incoming TCP connections. When you start up a node to join the network, it goes and fetches a bunch of peer addresses from DNS seeds. These are like DNS names like seed.bitcoinstats.com. And then once you connect to nodes, you get these messages. Nodes can send you these messages over the overlay network called the address message, which contains a list of like 1,000 other peers. And so you kind of learn about more and more nodes in the system. And what a node actually does is it divides the set of peers it learned about into 2 different tables called the tried table and the new table. And the tried table is basically known good peers. So every node in there has a timestamp, so you've talked to it at least at some point in the past. And it's divided up into 64 buckets of 64 entries each. The nodes are kind of hashed based on IP address, and the hashing is done such that for any given /16 prefix, it can only hash to one of 4 buckets. So the idea being that maybe if the attacker controls only a small number of IP prefixes, it's harder to like take over all of your buckets, right? But that's a dicey proposition, right? And then when you evict something from a bucket, you basically pick the bucket, you pick 4 random nodes. The one with the oldest timestamp gets demoted, which means you move it from the tried table to the new table. And then the new table is where you put all the new peers you hear about. So that's 256 buckets of 64 nodes each. And again, it's based on hash of IP address, but there's some bucketing so that if you but here the bucketing is based on also based on the /16 of the node that actually sent you the address, in the hopes that someone can't just completely give you tons of garbage for all your buckets if they send you a bogus address command. So when a connection is dropped, you reconnect to a random node, and depending on how many incoming and outgoing TCP connections and so on you have, you'll either connect to a node in the new table or the tried table. Okay, so that's how Bitcoin works. What's the problem? Well, the problem is that Bitcoin is vulnerable to these so-called Eclipse attacks, right? Where what happens is you use a botnet to own a whole bunch of different IP addresses, so you can kind of take over all the buckets, at least theoretically, and then you find some victim node and you connect 117 times. Every time it drops a connection, you're the next one in, so you're kind of monopolizing all the incoming nodes, all the incoming TCP connections. Then you give a bunch of address commands that contain only the IP addresses of your nodes. So eventually all the outgoing connections are going to be to your nodes. And you've now completely surrounded this node, and so you can kind of give it your own tailored view of the network. And so by controlling the view of the network, you can do things like engineer block races, like waste a whole bunch of CPU time by making a miner expend energy mining a block that's just going to be an orphan block because you prevented them from learning about a new block that they should be mining on top of. There's these selfish mining attacks where you mine a block, you don't tell people about it, and then you kind of make them waste time, and then you publish your block. And if you can do Eclipse attacks, it makes the selfish mining attacks much more effective. But there's an even worse thing, which is that proof of work is a consensus. As a consensus algorithm is actually completely unsafe in the asynchronous model, right? There's a fundamental assumption that there's only bounded communication delay between nodes. Otherwise, it's not a safe consensus algorithm. In particular, if an Eclipse attacker can impose arbitrary delays in communication, then what an attacker can do is, even without controlling any hashing power, they can kind of split all the miners up into different groups and therefore use the existing miners to mount a double spend attack by having them kind of for the good and well-intentioned miners actually creating a forked history. Okay, so I've been telling you all about SCP in the last few meetings, so you may say, well, wait a sec, isn't one of the big advantages of SCP that it's an asynchronous protocol, that SCP is actually safe even if there's unbounded network delay? And the short answer is yes, this is great. You know, unlike proof of work, these Byzantine agreement type protocols in the family of PBFT and SCP, they are safe no matter what the network behavior is like. So what's the problem? Well, the problem is that there may be layers on top of the consensus that are not safe in this asynchronous model. And so a good example of this would be, let's say you're using a blockchain to do payments, and you've set up an escrow account. So it's an account, maybe it's a multi-sig account. You require signatures from me and from you to access this account. And what I've done is I've sort of pre-signed some message that allows you to withdraw if you want. You can submit and withdraw whatever portion of this escrow account belongs to you. But in case you disappear, in 24 hours, I'm allowed to claim the entire contents of the escrow account for myself, right? And in that case, if I can prevent you from submitting a transaction for 24 hours, I can actually steal your money. And it doesn't matter that the underlying consensus protocol was safe, because the sort of higher layer replicated state machine had these things like time locked transactions that actually depended on time. And of course, for the other kinds of things that we're talking about using these global consensus protocols for, things like, software update logs or like revoking vulnerable software. These are all things where you don't want there to be arbitrary delays for actually getting the stuff out there. Okay, well, believe it or not, these overlay networks are like pretty well studied, and in fact, right now people are excited because of blockchain, but 20 years ago people were excited because of peer-to-peer networks, right? And so, in fact, there was a fair amount of work talking about multicast in that context. And so the kind of at the more tame end of the scale, there are people saying, maybe the M-bone isn't, maybe IP multicast isn't the right thing, and we should be doing end system multicast. And so the Narada work at CMU is a good example of this, where they basically formed a mesh network of like a bunch of nodes, and then they ran a kind of routing protocol on top of this, and you could set up a bunch of multicast trees, and it worked pretty well, but it was kind of intended for maybe like thousands of nodes, and there wasn't really an assumption of that there were malicious parties trying to attack this thing, or that there was like a large bounty involved in like denying service for a while. So that another kind of line of work that was a little more out there were these distributed hash table or DHT based multicast. So this is kind of structured multicast that is designed in such a way that it can scale to potentially millions of nodes, be very efficient, like you don't receive redundant copies of messages and stuff. But it was kind of brittle in the face of failure, particularly Byzantine failure. And we'll talk more about that in a few slides. And kind of as an alternative to the structured multicast. There is unstructured multicast, which are kind of these gossip-based protocols. And those tend to be more robust to node failure, but they're more wasteful. Like you might get multiple copies of each message. And whether or not they're scalable depends on whether you have a partial or a full view of the system. So in a full view gossip protocol, every node knows every other node in the system. And so if you scale that up to millions of nodes, it'll actually be a fair amount of traffic just maintaining this membership information. In a partial view, you only need to know some much smaller number of nodes that are sampled from the whole system. So again, maybe these are better for failures, but they are still vulnerable to Byzantine failures, right? Particularly the partial view model. Okay, so for anyone who came of age after the early 2000s, here's a review of what a distributed hash table is. The idea is, and examples of these are like Chord, Pastry, Cademelia is, I have up here, that's one that my student did that's used by Trackerless BitTorrent now. The basic idea is that every node in the system has a randomly assigned ID, which is like a 160-bit number, and it's basically a large distributed key value store. So if you want to store a particular key value pair, you hash the key down to a 160-bit number as well, and you store the key on the node whose ID is closest to the key, right? And close, the definition of close depends on the distributed hash table. With Cademelia, it's just XOR. So you take the XOR, and so basically if you kind of agree, if the key and the node ID agree in the top number of bits, then it's going to be close, otherwise it's not. And the way the DHT works is that you're a node, let's say this black dot node here, you need to know like at least one node who's not in your subtree at each level of the table, right? So here, you're this node here, and you on the right-hand side, so you have to know someone on the left-hand side of the table. But then you also need to know someone, say, you know, in this subtree that you don't belong to, and this subtree that you don't belong to. So what happens is, by knowing kind of log n people, one person who differs in 1 bit from you, going from the most significant bit at each level of the tree, you can route to any key in a log number of steps, right? So in this case, if the node ID is 001, or the starting node is 0011, and it's trying to find the key that's like 111110, right? And so, well, maybe it just happens to know one node whose node ID starts with 1, and that node is over here. It's a node whose ID starts with 101, but it knows someone in like a little bit closer, and this one knows someone a little closer, and eventually you get there in log n steps. So, so you can basically use this for multicast by doing this technique called reverse path forwarding. And so a system that did this was Scribe, which was a multicast that ran on the Pastry distributed hash table. Basically, your multicast group is named by some ID, and there's some node that's closest to that ID, and so that's going to be the source. You forward all messages there to start, you know, that's where they start for multicast. And then if you want to join the multicast group, what you do is you route a message to that source, and that route goes over kind of log n many steps, and the internal nodes that you talk to form kind of a multicast tree. And so with a nice kind of like log fan out, you're able to reach an arbitrary number of people in just, you know, any individual node only sending like log n times the traffic, and only log n depth in the tree. So one disadvantage of this approach is that it's unfair. If you're in the middle of the multicast tree, then you have to forward a bunch of traffic, and if you're a leaf, then you don't forward any traffic. So Splitstream, which is pictured up top here, kind of fixed this problem by saying instead of one multicast tree, let's have a forest of multicast trees, and we can stripe the data over all of these. So you can see any given node, like this node M here, is going to be a leaf in all but one of the trees, and then it'll be an internal node in one of the trees. So it's kind of fair in terms of the upstream bandwidth that you have to dedicate to this, right? So, and with striping, maybe you can also add some forward error correction, which would be good. Okay, so so the problem is that all these DHTs have a bunch of security issues. And there's a good ACM computing surveys kind of retrospective about all the security work a few years ago. and basically kind of divided it up into 3 categories of problems, which I think is about right. So one are Sybil attacks, right, which says that an attacker can join many times, and so basically overwhelm the nodes, overwhelm all the good nodes with the like virtual nodes controlled by the attacker. The other is Eclipse attacks, which are where you're kind of poisoning the routing table. And then the third are these rooting and storage attacks where you essentially engineer your node ID such that you control all the nodes near some important key, and then you can kind of throw away that key. So in terms of what this means for the latest generation of, I think, for the things that we're now interested in for that require multicast, Sybil attacks are potentially a big problem. When you look at everything that people did back in the day, you know, they did kind of admission control by assuming a certificate authority, right? We don't want that. They did stuff based on IP prefixes. That was not really good if you have botnets. They did stuff based on kind of network characteristics to like figure where you are in the network. But again, you know, with botnets, that's not so good. You know, there were actually protocols that like involved like examining the social graph, right, where maybe you like know some nodes. That seemed better. Like some idea, like Sybil Guard did this thing with like quotient cut and social graph. The idea being that groups of Sybils were probably not that deeply connected to good people. Proof of work, incentives. So some of these are relevant. None of them would really like totally solve the problem. I do think that with SCP, there's at least an existence proof that we can have decentralized protocols that invalidate assumptions of the Sybil attack, right? So what SCP does is, because it invalidates this, the Sybil attack paper assumes that you don't have any physical knowledge of the nodes who are your peers, right? That they're all just like these anonymous nodes out there. And with quorum slices, which I'll talk about SCP a little bit at the end, that invalidates that assumption. So at least maybe it provides some way to get around Sybil attacks. So I'm not sure how to do it for multicast. For Eclipse attacks, you know, a bunch of kind of, again, like analysis stuff that maybe is relevant again. For the rooting and storage attacks, I think those are less relevant now because that was when you were sharding your data out over a whole bunch of nodes. And at least in the blockchain space, we're talking about highly replicated systems where everyone keeps like a complete copy of the system. So maybe those aren't an issue now. Okay, so that was DHT-based multicast. The other whole group is these unstructured multicasts that are these gossip-based systems. So the basic idea is really simple. You kind of send every new message to k random peers. And so eventually this will, there'll be like epidemic propagation. This will just kind of reach out to everybody in the system. And after a few rounds, everybody will have heard this message. So the big problem is, of course, you have to pick these k-random nodes, and the obvious way of doing it, which is everybody knows all the nodes, it runs into scalability problems. So that's where this partial view idea comes in. A good example of a partial view protocol is the high-par-view protocol. And what that does is a little bit like Bitcoin. It maintains these 2 routing tables, like an active and a passive. The active peers that a node has is symmetric. So if you're my active peer, I have to be your active peer as well. And that's where you actually propagate this stuff. But then as soon as an active peer fails, you've got this kind of reserved list of passive peers where you can immediately find another one and plug the hole. The way the passive sets are maintained is through these shuffle lists. You kind of take a whole bunch of peers that you know about and pack it into a message, a maintenance message. And that maintenance message gets forwarded through like a random walk, like some number n of hops. So basically like each node keeps sending it to a random peer. And then when the time to live goes to 0, whatever that peer is, then processes that message, adds the nodes it learns about to its set, sends you back a bunch of passive nodes that it knows about. And if it has to evict nodes, then it evicts the ones that it just sent you, or you know, otherwise evicts randomly. And then the active set is maintained because like your TCP connection resets or something, so you know that node is not available anymore. Okay, so one problem with this kind of random approach is it's not necessarily very good for network locality, right? You can, for example, end up sending a message halfway around the world and back when it was just going to like another computer in the same room, right? Because again, you're just sending it to random peers. So this idea of having biased selection of peers, so that you can kind of bias your peer choice in a way that makes the protocol more optimal for the network. And what you want to do is kind of probably bias your choice of some peers, but also still have some random peers, so that if your bias thing makes it unsafe, you can always fall back on these other peers that really are random, and stuff still will actually propagate through the system. So a good example of a system that does this is XBot, which is an overlay network that has this strategy where, let's say you're some node I here, and you have one of your peers O, and you have another peer C that's not one of your active peers. You think C is better than O. You think you're closer to it on the network. So you don't want to kind of reduce the number of links in the system, because that would potentially hurt the availability of the system. So you want to kind of transform the graph in such a way that you're preserving the number of links. So you kind of go through this multi-stage process where what you end up is this other node C picks some node D that it wants to offload, and so you start out connected to O, and in the end you're connected to C, but then O is connected to D, so you haven't really reduced the number of links. So one question, this is obviously only done in the context of performance, but then it raises the obvious question: should we think about maybe biasing peer selection for security to make these things more robust? So another thing that people have tried is hybrid approach, where you have it's a gossip protocol, but it also uses some elements of the structured multicast approach. So like Plumtree is an example of this. That is that you separate your peers into like eager push peers and lazy push peers. And anytime you receive a message, you immediately send it out to all of your eager push peers, except the one that sent you the message, obviously. And then kind of in the background, you send not the full message to your lazy push peers, but just like some message ID. But that way, if there's some failure in the eager push peers, like people will still hear about stuff, and then they can request the messages. And you basically you start out and put everybody in your eager push peers, and then basically as soon as you hear a message multiple times, anybody who sends you a redundant copy of that message, all but the first person, you kind of downgrade them to be lazy push peers. And this is a symmetric relationship, whether you're eager or lazy. So basically what happens is you start out with this mesh, and very quickly it becomes a spanning tree. And then it can also repair itself fairly quickly, because you do hear about these message IDs in kind of batches in batch messages from your lazy push peers, and then you can also just upgrade a lazy push peer. You actually upgrade if you're missing a message and you wait for a timeout and you still don't get the message, the first person who told you about that message, you upgrade them to be an active peer. So again, this idea of maybe like disseminating message IDs, maybe if they're cheaper than messages, or some even more compressed version like a Bloom filter or something, could help identify bad nodes. How am I doing? You're good. Okay, good. So there's a bunch of other work on kind of secure gossip and secure dissemination of messages. This stuff, you look at the titles and abstracts, they sound pretty good, but it seems to be solving kind of like a different problem. So for example, there was this work on tolerating malicious gossip, but it's got the problem is set up in such a way that's very like sort of very much like the closed BFT model. Like you assume there's no more than T failures, and you assume there's some number K greater than T of nodes that are initially seeded with the ground truth and just need to get this out there. So I don't think these ideas are directly applicable. There's maybe some interesting techniques like path verification, where when you get these messages that haven't been accepted yet, you have a path of every place the message has been forwarded through, and so you try to get messages that have disjoint paths, because those are because then no single attacker could be messing with all of them simultaneously. Is there some way to adapt this to kind of irregular open membership systems like we're talking about here? I don't know, but it's something worth keeping in mind. There's a system called Fireflies, which was actually a multicast system specifically designed to, again, withstand malicious nodes. And the model is superficially appealing. You're saying, okay, we've got nodes that are correct, nodes that have crashed, and nodes that are malicious. But then it kind of assumes that that there's at most some fraction p of non-crash nodes that are actually malicious, right? So again, this feels very much like a closed system. The kind of key ideas involve nodes accusing other nodes and kind of broadcasting this information to identify who's bad and malicious. And then, of course, you have to worry about nodes bad nodes falsely accusing good nodes. So there's some way for good nodes to mask some number of accusations, but not too many accusations, and so on. And again, the idea of monitoring nodes sounds superficially appealing. I don't know if can we adapt this to something that doesn't require admission control? I'm not sure. Okay, there's also these intrusion-tolerant overlay networks, so the system called Lighton seems kind of interesting. It sort of repurposes research on ad hoc mobile wireless networks, all the packets are source rooted, and you have this failure detection based on kind of end-to-end checks of is stuff getting through. It seems, and then if there's a route seems bad, well, then you quarantine it for a while, and then it comes back later. So, first of all, this is geared towards unicast. It is good that it reacts well to these, to even a very high fraction of routes failing. But it also internally, under the covers, uses flooding to kind of get root messages out there. So that makes me think, well, is it going to be very vulnerable to like amplification attacks and stuff? It seems maybe a bit problematic. Okay, a couple of other ideas. So this was an idea that a student of mine had a number of years ago, Antonio Nicolosi. And this is more geared towards structured multicast again. But the idea is, let's say you really did have a structured multicast tree and you're reaching, millions of nodes, and you want to be sure that every node that's subscribed is getting what they're supposed to be getting, or else that there's some way to find out who's missing, so someone else can try to contact them directly. But you don't want to keep track of all these things yourself. So, we were thinking of this in the context of software update. If there's some critical vulnerability, you want to make sure all the machines running your software have been updated, or try to track down the ones that haven't been updated. And the way this works is there's two phases. In the first phase, you join the multicast system, and the multicast group, and this is some batch thing where you kind of create a new public key and you sign some certificate with your IP address, and then your key gets kind of propagated all the way up to the root, and what comes back is the hash of the root of some hash tree, and you can verify that you were included in this join request. And then in phase 2, every time the source sends a message, it gets back a bunch of acknowledgements. Everyone signs an acknowledgement, and the acknowledgements kind of get combined such that at the root, you only need to basically check one signature, or one signature plus check everybody who failed and has been removed from the system. The key idea behind this is that it leverages these signatures on gap Diffie-Hellman groups, which are groups where, if you have G to the X and G to the Y, you can't easily compute G to the XY, but if you have some number Z, you can tell whether that's G to the XY or not. And basically what these signatures have that's an interesting property is if I have two signatures on the same message, and I multiply the signatures and I multiply the public keys, what I get is a new public key that and a new signature under that public key. So you can see you can kind of basically aggregate all the individual nodes public keys as you're going up the multicast tree, and aggregate all the acknowledgements, which are just signatures. And then if there's anything missing, you can just kind of divide out the public keys of the nodes that are missing, but you can also check their certificates to know what their IP address was, and so you can have other people try to contact those nodes to get the message to them. So again, this was tailored to structured multicast. Can this be adapted to gossip networks? That might be an interesting question. Okay, kind of another topic is that applies particularly to these gossip networks is how do you actually how do you cut down on the amount of redundant traffic? And one thing that happens a lot on blockchains is you're kind of flooding transactions out there, and so everybody has a bunch of transactions, and what you really want is for everyone to end up with the same set of transactions, and ideally you don't want to have to send multiple copies of that transaction. So in these kinds of situations, what comes in really handy is if you have an efficient way to do set reconciliation. And so there's kind of obvious ways of doing it using hash trees to compare which parts are different, but that doesn't work if the differences are all over the place, or error correcting codes if there's small differences. But I guess like 8 years ago now, there's a really neat way to do this, that where actually the amount of network traffic that you send is only proportional to the difference in the size of the sets. And that is, the idea was that you use these things called invertible Bloom filters, where instead of just a bunch of bits, you keep counters, so that if you set a bit multiple times, you keep the counter. And so what you can do is you can basically take two invertible Bloom filters and kind of subtract one from the other to see which, and then that creates a new Bloom filter for just the things that are different between the two sets. And the other, you need one more trick, which is you need to kind of estimate the size of the difference, but you can do that by doing kind of like log many Bloom filter. So this is a pretty cool idea, which might come in handy in these systems. And then finally, of course, since like at least my interest in doing this is to get a good multicast layer underneath SCP, there's a question of should we be leveraging some of the kind of trust decisions that people are already making for SCP. And just to remind people, the way SCP works is that it forms quorums in a decentralized way by individual nodes picking these quorum slices who are the set of people that they don't want to be partitioned from, basically, the people they want to stay in sync with, and then SCP makes sure that that applies transitively. So every node in SCP picks a set of quorum slices, QV, and then a quorum is defined as a set that contains a quorum slice of every one of its members, right? So one question is, could you maybe subscribe only to the senders that you actually care about, have multicast groups, or maybe not even a multicast group, but some way for you to hear only about the people that you care about, but you need to care about people transitively. Like if I say, I'm only going to agree to something if Dirk does, and he'll only agree if Melinda does, then like I kind of depend on her. I need to get her signatures. And the other thing is, can you maybe leverage the trust that people are expressing in their choice of quorum slices? So in SCP already, there's this leader selection algorithm that depends on slice weight, which is the idea of what fraction of my quorum slices include this particular node, and that gives some indication of how much I trust that node. It's not great because you're kind of flattening this a lot of information that's expressed in a quorum slice into kind of this one number, but it does provide some indication. So kind of in conclusion, I think a very large number of the kind of interesting protocols that could come out of this working group will actually end up needing some kind of message dissemination system. And it'll have to be efficient and scalable to many nodes. It'll have to be obviously self-organizing and not depend on a central authority. And it will have to be Byzantine fault tolerant because otherwise the systems will end up being vulnerable. Currently, there's basically this big trade-off between you could make a secure one in which you send a whole bunch of redundant messages, like everybody sends everything to everyone. You try to make it scalable, then it suddenly becomes vulnerable to Eclipse attacks and stuff. We've got kind of individually building blocks for efficiency and scalability, like DHTs, peer sampling, bias peer selection, things like that. We've got building blocks for security, things like path verification, the idea of monitoring the ACK compression, quorum slices, but we don't yet have a good way to combine to achieve all these good things at once. I think this is an important open problem for the kinds of stuff that we care about here.
Cool, thank you. That seems to be a really useful survey. I'm sure people must have questions and comments.
Actually, I have a question. And where do things stand in terms of your own work? And do you have people working on this Is there something you can bring us? It's a real
Uh,
question.
Not yet. I want to work on this. It's kind of where, like, if I got requirements or something, like, if I got a sense of requirements and stuff, that might guide what I'm thinking about.
Hi, Marie-Josée Montpetit, MIT. I'm on the side of the room and I see nobody. Actually, when in MIT we had done a peer-to-peer video distribution network based on peer-to-peer distribution, adding FEC to it. Actually, we could actually get some kind of, I would say, low-level security just by doing some short encryption on the FEC headers. And if you didn't know what this key was, you couldn't decode anything else. And it was really, really good to send messages across the network. Yeah, it was like, I would say, a coded type of DHT, but it was really good, but it was not really, really secure. But it would be a good way to distribute stuff really fast.
I think the security you're talking about is confidentiality, which I haven't even touched here. Like, I'm actually just worried about availability.
Okay, because that actually would
here.
be something interesting to investigate.
Yeah. So
in the context of this group, because a lot of time you may need to have, I would say, some low-level privacy or low-level security to the stuff you're sending. You may not need to have very high encryption problems that actually will just increase the latency of your distribution. So maybe that's something that could be interesting to look into. Thank you. And I'm going back into the dark hole.
Tobias Gogomus from LMU. One question, have you considered the stuff the people in the message layer security group do? Because they do some kind of group key agreement.
Yeah, so again, this isn't, I'm not even thinking about confidentiality here.
Okay.
Like, in the context of Bitcoin, like, you don't need confidentiality. You just need to make sure that, like, people can't double spend, right? And that's the level on which these things are currently vulnerable. So, like, think about if we used like a global consensus protocol to do like a new version of certificate transparency, right? There wouldn't even be confidentiality requirements, right? But it's availability, right? If we use this for like certificate revocation, right, you need to make sure those revoked certificates get out there. So, so again, like, yeah, we could maybe think about adding that to the to like list of requirements. It'd be interesting to, it'd be helpful to get a more concrete problem that this would be used for.
I'm more thinking not about this confidentiality, more about the techniques they use to distribute the keys.
Mm-hmm.
Because they're
do you want to say? So I'm not following that work. So
okay,
just maybe great to hear how you think that could apply.
Just a feeling. I'm not so familiar with it.
Okay.
Just a feeling. I saw it yesterday and I saw yours, so it's kind of similar.
So there was like there was this work at Cornell where, like, what happened was it kind of broke the identifier space up into kind of these clusters. And what happened was every time someone joined a cluster, you kind of shattered it and like reorganized everything using some kind of like, secret shared, like, but verifiable random function like thing. And so maybe in terms of like organization, if like, I don't know where my node ID is going to place me in the multicast tree because there's a threshold thing, like maybe that could actually be useful. So I should check out if there's so which working group is that?
The MLS, message layer security.
Okay, cool. Thanks for the tip. Other question?
Just one question from my side. Have you looked into the combination of ICN and dataset synchronization? So like NDN and partial sync and these protocols?
These are for like set reconciliation?
Well, they probably do more than what you need for buzzer protocol.
Yeah, so I guess I should check those out. And what do those? So those are like drafts or RFCs already?
Papers, and I mean the NDN project.
Okay.
Yeah. So I mean, CCN or NDN style ICN kind of has a implicit multicast distribution.
Right.
But has public key based certificate infrastructure behind it.
Right.
So it's probably more than you need here, but dataset reconciliation.
And so there's admission control through the certificate system.
Well, there is more signing of messages and certificates behind this. So.
Okay. See if that, I should check it out. See if
Okay.
anything applies. Thanks.
Great, thank you. Thanks again. Just a quick logistic things. There are people standing in the back of the room, and I see some empty seats. So if you want to sit there, maybe raise your hand if there's an empty seat next to you. Yes. Maybe this one is a bit tricky. And the other thing is, where are the blue sheets? Okay. Who hasn't signed the blue sheet? Maybe keep them, yeah. Quite a few people on the right-hand side. All right. Moving on with Christian and the GNU name system.
Okay, well,
Do you have the ticker? Yeah.
yeah, I have the ticker. Well, thank you for inviting me, and also want to specifically thank David. He gave about half of his material that he gave is great background for what I'm going to talk about. So I hope you understood most of it. That's going to make my part much easier. So to give some background, just like David said, this whole thing comes a bit more of 2000s, where peer-to-peer was in vogue, and we decided that this internet wasn't decentralized enough. And then a couple of years later, people felt that this was also a bit too surveilled, and well, we had always tried to build in more encryption and more privacy. And so this GNU name system comes out of the GNU-net project, where we have built things like distributed hash tables that you just heard about, and gossip protocols and flooding protocols, and all of these things that he's mentioned are in there, and part of it is being used by the GNU name system. Now, in GNU-net overall, we're building a couple of other things. So if you're worried about the internet having been broken in Europe yesterday, there might be anonymous publishing for you in there. We do IPv4, IPv6 protocol translation in case this hasn't been solved yet. And GNU name system, I have to apologize to Martin. I'm not mentioning reclaim ID on this slide yet. So we also have identity management on top of the GNU name system, which again relates to the next talk I hear. So lots of other things in there, but today I'm going to focus on the GNU name system for you. So our motivation is basically, well, when you build a new internet, DNS isn't exactly what you want to start with for naming. We have these problems with traffic amplification, with censorship, with mass surveillance, cyber war, and we didn't want to go for the band-aid solutions, DNS over TLS or something like that. So GNU name system, first thing is we said we wanted to decentralize, so no more hierarchy. So this is a big disappointment for some of you. The names are not necessarily global. That doesn't mean we can't have a consensus of basically saying, okay, Stefan gets to run .fr for us, that's okay. We just have to put into our configuration his key, and then he can control .fr. But in principle, anybody can, run their own root zone. So you can think of this as the extreme version of hyperlocal, so hyperlocal, where you have your root zone on your machine, but you can, of course, delegate .fr to Stefan. And yeah, you're very welcome, Stefan. I think you're doing a good job on that one. We can still have globally unique identification. So if you put in a public key as a name, well, that's still a globally unique identifier. So we distinguish between identifiers, which are things we can't remember, and names, like, I can remember ethnic.fr. I can't remember Stefan's GPG key. Too complex. That's an identifier. The biggest difference to DNS is we have query and response privacy. So as you'll see, when you ask a question to the GNU name system, the infrastructure, even the server that stores the answer, doesn't know what the answer is or what the question is. It's encrypted. They can't see it. They can just say, well, this is the answer, encrypted, to your question. I don't know what you asked for. I don't know what the answer is, but here's what you wanted to have, and then you can decrypt it. Right? So it's much better than TLS. If you do TLS, in the DNS context, the server at Cloudflare can still see what your question is. It can still know what the answer is. In our case, it can't. Right? But it can verify that this is the correct answer to your question. Now you might say, how is that possible? Well, we'll get to that. So the result is we get also a public key infrastructure. It's all signed, so DNSSEC ++, so to speak. And we can use this for identity management. And best of all, it's interoperable with DNS. We have a proxy DNS to GNS. runs on port 53. You can send it DNS queries, you get DNS answers back, but internally it may use the GNU name system for top-level domains that are configured to use GNS. Should mention this is a joint work with Martin Schanzenbach, so other parties to be blamed are in the room. Don't just beat me up. Matthias Wachs and Patrick Gerber, who couldn't be here. Now, I've always been told if you won't get anything out there, you have to make sure it's usable. So I'm going to start with the user experience side. So here's zone management. Basically, we have a graphical user interface. You can also do this with command line if you prefer, where you can enter records. So for example, here I'm creating a new zone. I called it RMS for fun. And then when I created a new zone, you see here now there's a public key for that zone. Now I'm going to go here, type in a name like GNU, give it a record type. So we have supported some of the canonical ones in from DNS in our user interface, and then some new ones for the GNU name system. Now I can type in, the usual information. I can type in an expiration, right? Can add TLSA records. For that, for example, I can go and type in here the domain name and click connect. Then it will do a TLS handshake and obtain the TLSA record automatically for me. So somewhat easier than what I'm used to with most DNS software. And then I have, for example, here the A record and the TLSA record for WW in the zone. What then happens is basically I have my zone, or Bob has his zone here, right? And once he's done this, he can reach his zone under www.bob, or in this case, www.rms. I have my public key. I need to introduce myself to other people if I want to have a secure channel. So maybe I go to Stefan, who is running .fr. I'm going to tell him, hey, this is my public key. Please put that into the zone file, delegate this domain to me. So he would put, well, he's now Alice. Sorry, Stefan. He would put, my name into his zone file with my public key. So that's the equivalent of the NS record in DNS, right? So in DNS, he would put the IP, well, the host name and then the IP address of the authority. In our case, he would just put the public key, right? So a bit simpler. You don't have to teach people about glue problems. Much less work for Stefan. He just puts a public key. He only has to put one record. And once he's done that, the delegation works, and alice.bob.ww would delegate to my website. So how does the name resolution work? Well, again, we have the two parties here. Bob has his zone, Alice has her zone, and Bob will periodically put the information from his zone into a distributed hash table. Remember what that was from David, right? Key value store. In our case, we use a 256-bit space, not 160-bit space, but that's okay. Underlying, it's a variant of Kademlia, so he'll be also happy with that, right? It's a variant because we do some randomization to get around a couple of the Eclipse attacks a bit, but it's close, right? And we have the logarithmic performance, logarithmic connections, all of that is there. So no worries here, Stefan. And so we put this information into the DHT, and when Alice wants to figure out who is www.bob.alice, well, she'll first find out, well, who is Alice? Who's Alice? She wants to know. Well, she knows she's Alice. She knows Alice is in her GNS system. It's not DNS. So she goes and finds in her database Bob's public key. Then she goes into the DHT. So you can think of it as a local cache. Goes into the DHT and says, well, I don't know what this, WW under Bob's public key is, and gets back the answer from the distributed hash table. To make this practical, here's how you can do it. Here's the Mozilla Firefox. You go into your preferences, set network settings, set a proxy for SOCKS proxy. Make sure you proxy DNS when using the SOCKS, otherwise it kind of doesn't work. And voila, you can do www.rms or something like this and resolve the names. And you can see here it's verified by GNU, right? No longer let's encrypt there because the man-in-the-middle TLS proxy has basically verified the certificate of the website against the TLSA record, right? Finally, TLSA is working for everybody, but then synthesized a new certificate against the web browser saying, yeah, you trust me as your proxy, and I have verified, so now it's being verified by the GNU name system for you. Right, so this is actually working. I should mention this whole manual configuration Martin has made obsolete by having a little plugin in the browser where you can kind of say just configure it, enable it, and it should be way more automatic in case this was too difficult. Okay, now we have a little privacy issue, of course, and a security issue. If I just say, okay, I'm going to put this information to the DHT, everybody goes and says, well, okay, now how can I trust this DHT? Basically, instead of being able to have any DNS operator modify the answers and monitor my traffic, now I have a billion peers in the DHT that can do the whole thing. It doesn't really sound like a security gain here. So I'm sorry, we have to get to crypto. I'm going to try to do it slowly here. So in crypto, we're using elliptic curves. So for an elliptic curve, we have something called a generator. We have the size of the group, right? So that's some number n. It's usually a prime, should be a prime number. And then we have a private key. That's just some scalar modulo n. And then the public key is basically we have on the curve, we have an operation to add points to themselves. And if I add g x time to itself, I get another point. So point addition gives me a point. That's group operation. And so the point P is defined as adding g x times to itself. And that's then the corresponding public key to the private key x. And basically the security assumption of the elliptic curves is that it should be very hard to get x from P. You know, G is public, everybody knows G, everybody knows N, everybody knows lots of other group parameters, but as long as you don't know X, you can't kind of do P divided by G. That's the hardness assumption. You can't do this efficiently, I should say. Yeah, well, 2 to the 128 operations, and yeah, fine, and don't do it. So this is just really, this is nothing GNS specific. This is just, any usual elliptic curve cryptography that hopefully you're somewhat familiar with. If you're not, just trust me that this works. And it works pretty fast, 100,000 CPU cycles for the point multiplication. It's not crazy inefficient. Okay. So now for the DNS side, if you're thinking DNS terminology, well, we have labels, right? So these 63-bit things between the dots in DNS. Now I'm going to interpret those as a number modulo n. So if you say, well, but www isn't a number, well, hash it modulo n and you have a number, right? So that's what I call a label. And then in the end, we still want to publish records. And we basically said we're going to do DNS compatibility by saying if the record type is below 65,536, it's a DNS record type, and we're going to have a 4-bit field. So if it's above that, it's a GNS-specific record type. So the DNS people can continue allocating record types, and there won't be any conflict with ours. But so we have record set of records. So this is, IP addresses, TLSA label records, whatever else we want to publish in there. And this is just in the clear text, in the zone under the public key P for the label L. So every zone, we don't no longer identify as a domain name, we identify the zone as a public key. So the public key tells us which zone it is. Every zone must have a public key, just like in DNS, every zone must have a SOA record. Okay, so these are the in clear text records in the zone P under label L. Okay, now when we want to go out there and ask the DHT for information, well, the DHT looks up things by a hash. All right, so we're going to call the hash that we're going to send out for the DHT to query for records, the query hash, so Q, for the public key P under label L. I'm not telling you how you could get this yet. I'm just telling you this is what we're going to send out to the network, right, to get this information. And what we're going to store in the network in encrypted form is what we call a block of information. DNS has these strange 512 byte limitations. In our case, we said, okay, 64 kilobyte is the max. It seemed a reasonably sufficient number, but maybe in 20 years they're going to tell us, why did you only pick 64 kilobytes? But it's not supposed to be for publishing files. It's supposed to be publishing metadata, right? So we have the encrypted information for label L in zone P that we're going to publish under QPL. That we're going to call, so this encrypted thing is we're going to call BPL, right? So that's what everybody can have. It's just encrypted. You shouldn't give any information from that. Okay, that's the terminology, just so you know what the various things mean. Okay, so how are we going to do this? If I want to publish the records, I know them in the clear text as RPL, right? I'm going to first do the hash of the label and the public key. Right? So take the label and the public key, hash those two together. Call that small h. That's a number. And then I'm going to multiply that number with the private key of my zone. Remember, x was the private key of my zone. So multiplying two numbers gives me a number mod n. And that turns out to be another private key. Right? D is still a private key. So I can derive one private key from another private key. Now notice, D is literally any private key. If you don't know what H is, and if you don't know what L and P is, you don't know what H is, you have no relationship, there's no clear relationship. If you want to get D, you need to know X and you need to know H. Right? So D is just as secret as X was. Okay? So now I'm going to do is I'm going to take my records and I'm going to encrypt them with symmetric encryption using an encryption key that I've derived using a hashed key derivation function, so fancy hash function, also from the label and the public key. So if somebody doesn't know the label and the public key, somebody is not able to do, enumerate the zone, somebody doesn't know the zone public key or doesn't know the label, either one of the two can serve as a secret, they can't decrypt this. Agreed? Right? Symmetric encryption is a key. If I don't know what the inputs were, done. Okay, so I'm going to encrypt the records with that, and I'm going to sign it with the little d. And I'm going to attach DG, which is the public key corresponding to the signature. Right, just like XG was the zone key, now I have DG, public key of the signature. That's the block. And I'm going to publish this under the hash of DG. What does this mean? Well, if I'm in the node, I'm a DHT node, I can check that this BPL should be published under QPL because I can check that DG hashes to, H of DG. That's a very trivial operation. And I can check that this signature matches this public key. So it's a well-formed record. Now, if you are not in possession of the X, you can't create this record. So I also know it comes from some zone. But I cannot figure out what the zone is. Again, based on the security assumption of the elliptic curve, I can't divide this DG by P, so I cannot know, what the label is, or what the public key was, or what H was. I can't even tell which zone this record belongs to. Right? So I have to be neutral infrastructure. The DHT can't know for whom it's publishing records. It doesn't know what it publishes. But if it returns these things, well, anybody can check. And if Stefan gives me a wrong record, I go and say, Stefan, did you not check the signature? Right? Now, there's one thing we do put in the clear text here that I'm kind of omitting here, which is there's a timeout value. I can say this thing should only be valid in the network for whatever 2 weeks, right? And then afterwards, everybody should drop it. But this timeout value is really not security sensitive. It's more, housekeeping. Now, if I want to search, I don't have the private key. But I assume, again, I know the zone's public key. Remember, .fr is in my root zone, so I have the public key of Stefan in my keyring, maybe gotten by default as my operating system, just like every good recursive resolver has gotten some trusted root zone. So I have P, and I've guessed the label is ethnic. Right? Somehow I magically knew that one. If I don't, I have no chance. If it's a password, he has to give it to me to let me have access. So I know the label, I know the public key, which means I still can compute H of L and P. So I can get my small h. And now comes the magic. Really complicated magic. I can compute H times P, right, on the hash of that, which is the same as H times X times G. What? P was XG. Very complicated math here. And then this is the same as H times DG by definition of D. Right? So I get the same query, right? H of DG is what it was published under. I can compute H of hash of HP. So I can ask this question, and of course I can check the signature myself, and I can do the decryption. If I know the public key, and if I know the label. If I don't know either of the two, I get nothing. I can check that this is the right answer. I can't decrypt it. So basically the only way to get information out of GNS is to know the zone's public key and the label. And of course, I can learn public keys over queries for other zones first. So I have query privacy, response privacy, and signatures in this system. Okay. Now, we also can have, as I said, global unique identifiers. Very simple method. You just take the public key and append it at the end. With elliptic curves, fortunately, that barely fits into a label. So we can just put a public key at the end and we have a global unique identifier, just nobody can remember it. But if you do need this in some kind of application where you're going to say, I need global uniqueness, well, as long as you don't expect users to remember these things, you can just form something like alice.bob.public key and it works. We're also worried about key revocation. So for revocation, you basically sign this with your private key. This zone is no longer valid. You mentioned flooding earlier. You know, we flood it basically over the links in the peer-to-peer network, over the DHT and other links if we have more. Now, we use Epstein, efficient set reconciliation. You mentioned that earlier. For peers being offline, if somebody reconnects and has missed some floodings, we use this efficient set reconciliation to kind of get the missed revocations across. To prevent the DDoS potential, you mentioned flooding is bad for DDoS. You have to do a proof of work calculation. You mentioned that as well. Before you can revoke a key. So basically, if somebody just goes, oh, make a public private key pair, revoke it, and does this 100 billion times, well, they could also just mine Bitcoin instead. And we try to basically make the cost of doing a revocation CPU-wise expensive enough that this is not effective denial of service vector. Of course, you can do the calculation ahead of time. So if you're Stefan, you're running .fr, and you go and say, if I'm compromised, I can't just say, well, I have to wait a week for computation before I can revoke. Well, just make your proof of work calculation ahead of time and only then go live with .fr, Stefan. Right? Easy to do. And yeah, of course, you can store the revocation itself offline in case you don't want to be hacked and have your zone revoked by accident. Okay, so revocation is in there. Now, I have to thank the IETF for the more recent developments. So initially, we had proposed to use .gnu as a protocol switch, right? And as Warren here observed, this is how you should do it in his RFC. But as I said, he's wrong here. You know, we asked the IETF, please reserve .gnu, and following the usual IETF way, they didn't follow their own process. And so we decided, okay, if we can't get .gnu, we're just going to take everything. So the latest implementation that we have released basically allows a user to override any domain name with the GNU name system. Just put in the public key that you want to have for any domain name, and it will go to GNS instead of DNS. So we're no longer looking for, does this end with GNU? And the very nice effect was we did then usability studies, and the users love it. They can't even tell they're not using DNS anymore, right? Now, as application developers, you may not like it so much, right? But for users, you know, it's great. But we have a DNS proxy, so as an application developer, you can also no longer tell if you're using DNS or GNS. It depends on what your network provider or your user has configured. Maybe there is privacy, right? That's a slight disadvantage. As a user, I generally like to know if I have privacy or not, but here it's now completely intransparent. On the technical side, we did demonstrate that our DHT scales to millions of records. David will not think that that's a great surprise, but you know, you have to do some tuning before you can actually show this. We implemented a net zone import to basically, given a list of .fr names, hit Stefan's servers until they give us all the information, because .fr does not allow zone transfers, so you can just brute force it if you have a list of names. Very strange that they publish the list of names but don't allow zone transfers for .fr, so you have to ask for every single one what's the DNS information. We also implemented Ascension, which is a tool that does proper zone transfers, so slightly more efficient, and used that to import .se and .bfh.ch and made sure that basically all of the record types we find in all of these three small zones are supported by our system. Okay, so to conclude, DNS monopoly is over. GNS is simpler than DNS. No more glue, no NSEC3, no RR6 are required. We have private name resolution, censorship resistance. If Stefan blocks you, I can just put your zone in directly and I'm fine. We don't require ICANN or a root zone or IANA special use TLD. You just take everything. And if you previously saw about the GNU name system and you told people, if you see .gnu, that's special, forget about that. Now teach people about that there could be other protocols than DNS for name resolution, and they just can't tell. And if you want to get your top-level domain and you're a member of DNSOP, you know, we welcome your donations, just like ICANN welcomes your donations. It'll help us scale our infrastructure. Thank you.
All right, thank you. Are there any questions?
Yeah, David.
Yeah, can you say a little bit more about how adding a little bit of randomness thwarts the Eclipse attacks on Kademlia?
Yes, so basically what we do is we first do a random walk over the peer-to-peer overlay network and then start the Kademlia, let's say, gradient descent. Greedy.
But
algorithm. You can still have Sybil. I'm not saying we're solving all the problems. You're solving specific Eclipse attack problems that way. So Sybil attacks, if you have a very large number of Sybils, are still a theoretical issue. I don't know if we're in practice going to have that many Sybils, especially once all of the DNS operators run GNS DHT nodes on their fat DNS servers. That's my hope. But it addresses some concerns, right? So you do this random walk first, and for the random walk, you need to know kind of what the size of the network is. So we have a network size estimation algorithm to get log n of the network size, and if you do log n hops in a small word topology, you had a random starting point, and thereby, and if you do this every time you do a query and you do it repeatedly, you start from different starting points, and you end at different places possibly, and so a Sybil attack becomes less effective. An Eclipse attack becomes less effective.
Reminder to identify yourself at the mic. Okay.
Hi. My question is about what would be the information
You
inside
are?
the key.
Your name, please?
Oh, sorry, Shubir. My name is Shubir Ali. Okay, so my question is, what would be the information inside the key? If the two nodes are running in the cluster, right? So the active node is got failure. So how would the second node work with the key?
I'm not sure information. The key is just a public key or a private key, or I'm not sure what you're.
Actually, the machine is running the zone is running on the machine, right?
If you're running a zone,
Yeah.
You're basically taking all of your record sets,
Yeah.
and you periodically publish them into the DHT in an
Okay.
encrypted form,
Okay.
right? So even if you go offline, the DHT will cache that information for some amount of time.
Uh-huh. Okay.
Does that help?
That's all.
Giovanni, SIDN. So I'm also a researcher, and I'm a DNS guy, and I work for an operator, so I have to disclose that. I'm always excited about seeing new naming systems. For me, like DNS, it is nice to see new name system, but the real thing of the DNS is about high availability and high performance that it can deliver. It's not only the name system. That's very important. If you want to propose something, you need to do what you're doing. But I think your real enemy should be something that you can deliver high performance availability that DNS can deliver of any cast replication, caching, and a bunch of other stuff, and trust, and gain trust of the people.
Of course, but caching we can do in the same way. The DHT caches records, intermediate nodes can cache records, and DHTs can be high performance. And unlike DNS, we don't have problems with out-of-bailiwick, so we don't have as many redirections. In our case, caching is also implemented on the client side, right? So end-to-end side, so we can have possibly, if you have frequently used names, they might already be cached locally. So caching is still considered in the system. In fact, we have some additional features I did not mention, like when in DNS you time out a record and you go down to time to live 0. Then kind of all the caches become stale, have to drop all the records. In our case, you can already tell in the records that, hey, this record is going to be valid after a particular point in time. So I can pre-populate caches with information that will be valid in the future ahead of time, which is something DNS cannot do. So we've got some features to actually do better in caching than DNS.
Yeah.
And performance-wise, I don't see how we inherently are worse, but of course we do inherit availability and performance properties from the DHT. But DHTs aren't necessarily super slow.
So maybe a thought exercise for you folks for next, continuing this work, how would you compare if you would run .com with more than 100, if you would run .com, which has more than 100 million domain names on it, and allows for dynamic updates and delivers very fast response time. So maybe something you want to consider in the future.
Well, one of the things we have seen is in terms of importing large zones, most of the churn, we studied .se for that, is in the RR-SIG records. And so since we don't even have RR-SIG records, most of the churn of the DNS system won't even touch us. And the import cost primarily for us is doing the signatures. And well, if you have DNSSEC, the signatures you use there will be more expensive than EDDSA signatures that we use. So there, again, don't see a problem with significant updates. Of course, if you have things like DIN DNS, where you have people changing their IP address every couple of hours, that'll be harder with the DHT, I agree.
Thanks.
And one thing we also can't do is using GNS to do things like configuring DOH over DNS. So .rpar reverse lookups don't exist in our system.
Just quickly, we have to close the line after the last speaker, after the last person.
This is Ulrich Wisser from the Swedish Internet Foundation. We are, of course, happy that you used .se for your tests. And But I would know if let's say I would like to go to the IETF's website using the GNS, then if I understand you correctly, I would need the IETF's public key first.
No, if you have the public key of .org, and .org has the public key of IETF, it will still work fine.
Right. Then I have to have the public key of .org.
Right. And if .org supports GNS, we would of course put this into the default configurations, just like you would do with HyperDNS, and everybody tell who the .org's name servers and IP addresses are. Right.
Okay.
Now, if you go and say .org does not support GNS, but IETF.org does, you could put into your configuration saying IETF.org is this public key, and basically only slice out this part of the namespace for GNS and leave .org with DNS.
Okay. But that sounds.
Yeah, you start with like a
that
host file,
sounds
but that's hyper DNS, right?
That sounds awfully that you suppose that we would make another central organization to collect these public keys that you want to distribute to everybody.
We allow you to automate that process because we have this idea of curved DNS. We stole that from Dan. Basically, if you call your name server something that has a public key in our format in it, we'll just say, that's your public key. So we can kind of steal that information if you provide it.
Okay, thank you.
Wes Herdiker, ISI. Zero hats on my head at the moment. I have a lot of them that might relate, but really cool math. I mean, I think that the math behind this is really slick. And so my question is more about, especially the screenshot of the web browser showing the RMS page, for example, and the usability of how you might get there, because, yeah, that one. So if I'm understanding this right, there's sort of this new global collection where you might have a whole ton of essentially, I don't want to call them roots, they're public keys, and under which there's a whole bunch of names.
Yeah.
And you're going to collect all of these public keys on your system, and maybe there's hundreds, maybe there's thousands, maybe there's millions, maybe we each have one, which is really kind of cool.
Well, the idea is everybody should have one, but you don't need to, you can have global names, which are kind of like the consensus. We all agree that we put those into our configuration, and then there'll be local names. So maybe I put RMS into my configuration, but you don't. And then we can't use the RMS names as global names. We'd have to do whatever, www.gnu or rms.gnu.org. Right? But if I go and say, well, I like this website and it has been censored by my government, but I have its public key, I can just put that in and bypass the censorship operation.
Right? So that brings me
kind
to
of have both. We have a
right. So I understand that. So that brings me to my question, because there is no definition of a global name. You sort of stated that actually on the first slide. Don't go back there. But
no, global names comes from global consensus. Another question is, how do you, who do you get into the global consensus?
How do you get to global consensus? So the reality is that the URL, my question is actually related to that URL, which makes it look like you have no notion there of what public key is actually serving that global name. So, I mean, the reality is I would expect from a usability perspective when I type
this is not a global name. This is a local name. So I have RMS configured on my system.
Right. So as my application level, if I put in RMS, I'm going to go search through all of my public keys and look for RMS under each one. Which one do I pick? Which one do I get?
No. In the configuration, you say .rms equals public key. You locally as a user give each top-level domain name that you want to capture, assign it to a public key.
And you can have conflicts.
You can assign one public key per top-level domain. You can assign the same public key to multiple top-level domains if you so choose.
So you have to manage that list.
Well, I would assume that for the global consensus, you get a sane default, just like your network service provider gives you a sane default for the root zone.
I look forward to that consensus process.
I assume we will descend on that.
So Warren Kamari, Google, also speaking without any hats. A couple of things. First, your URL at the end, unfortunately, is incorrect. I think you need to add old.gnunet.
Yes. Yes.
Just so people want to find it.
Yeah. Thank you.
So I understand that kind of part of your design goal is to not have a centralized system, right? You end up with a consensus-based thing. Let's say that RMS ends up being a consensus global name. That's really great, and everybody who's using the GNS system can use it. What do you do when, for example, the other users of the namespace, like the DNS, end up trying to use RMS as well? You're going to end up with And or
We generally would say we advise ICANN to not assign any more names.
that might
We were told the same thing from
sure,
IETF before, and so now the advice is the other way around.
okay.
Any name they might assign from now on is likely to be a conflict with some user.
Okay, that's a perfectly fine answer.
Thank you.
I had a third point, but I don't remember what it was anymore.
Okay, that was fun. Thank you very much for bringing this to us.
You're welcome.
So I need 1 minute to set up Nathan here, just bear with me. I don't know. So if you want more space next time, be sure to sign the blue sheet. And Nathan, I have your slides up. Are you in the queue? So you need to get into the queue, right?
That was the way it used to be. Yeah, it's.
So Nathan, I'm getting you on.
Okay, can you hear me? Hi.
Yes, we can.
Okay, great. Okay, can I control my slides from here?
I don't think so. You have to
No,
tell.
I don't.
Sorry for that.
Sure, sure. Okay, no worries, no worries. Okay, hi everyone. I hope my voice is coming through well.
Yes, it's good.
All right, great. Okay, so I'm Nathan. I'm from Singapore, and today I'm presenting on Byzantine Agreement protocols for large-scale decentralized identity management. So let's go on to the next slide. Hang on. Can I? All right. Okay. So to just give some context, in the last IETF presentation in Bangkok, I shared on how decentralized identities, SSIs, in short, could help address the issue of data breaches and the challenges and constraints, right? Of course, the details are over there. And you can find the link over there, which goes to the last presentation that I had. Okay, so we talk about scalability, we talk about privacy protection, we talk about interoperability across various decentralized platforms, right? These are the things that we discuss from a very high level and some of the possible solutions, perhaps. So in the next slide. Okay, so this is my brief introduction. I'm a research engineer with one of the local banks in Singapore. And this is my background. I sit on the Hyperledger ERC 725 Alliance and work with the global folks on some of these blockchain solutions, right? So this is my profile. You can access it. Okay, next slide. Okay, next slide, please. Yes. Okay, so one of the things that we have identified, myself and my team, is that for any large-scale cross-border decentralized identity management, 3 attributes are necessary. And this is called the in popular terms, right, the blockchain trilemma, right? It has to be sufficiently decentralized, i.e., borderless, and of course scalable on a planetary scale. Imagine onboarding billions of people onto the blockchain, right? Identities, right? And of course it has to be secure. So this is the trilemma. I think most, if not all, guys who are privy to the decentralized space would know, right? Correct. So this is the trilemma. You can only choose 2, right? Either scalability and security, or scalability and decentralization, right? Okay. Next slide, please. Next slide. Okay. So to quote Vitalik Buterin, right? Blockchain systems can only at most have 2 of the following 3 properties, right? Correct. Scalability, decentralized, or scalability and security. Next slide, please.
Yep.
Okay. All right. So from the last presentation in Bangkok till now. There are many promising developments which were ongoing then and still ongoing. And you can see on the slides, Cosmos, one of the interoperability blockchains, have so-called mainnet has launched, and of course you have DIF, Decentralized Identity Foundation, extremely promising. Many organizations are involved in coming up with the DIDs and the overall solutions, architecture for decentralized identity platform, right? And of course, Algorand, right? A very promising blockchain protocol, right? Which promises to achieve the three of mentioned points: scalability, security, and decentralization, right? And of course, Vault. You can see many of these news are offered. So in my role is to explore how these developments, right, could help, and how my organization could react in time, right, to be on board this whole decentralized identity movement, right? So next slide, please. Okay, so this is a sample view of a decentralized identity ecosystem. Today I'm going to talk about the ones highlighted in red, right? You can see this is the one of the sample view proposed by Microsoft, right, of the decentralized identity ecosystem. You have your people apps, and you have a DID authentication, which I'll talk about briefly later on. And then you have, of course, the decentralized platform, the blockchain itself, right? So how do we achieve scale at that on the decentralized tier is the question that I hope to share with everyone today, right, through the slides, right? Next slide. Okay, so the DIDs, at a superficial level, a DID is simply a new type of globally unique identifier, URIs, right? But at a deeper level, DIDs are the core component of an entirely new layer of decentralized digital identity and public key infrastructure for the internet. This DPKI could have as much impact, on cybersecurity and privacy as the development of SSL-TLS, right, which we have today. So a sample of DIDs is shown over there: URN, UUID, and of course a namespace. For some DIDs, you could point to the Ethereum blockchain or the Bitcoin blockchain, right? And the user can have more DIDs, and of course DIDs are not limited to an individual. Object can also have a DID, right? An IoT device, an Internet of Things device could have a DID attached to it. Okay, so this is DID in short. Let's go on to the next slide. Okay, next slide. Okay, so how Ethereum is approaching the whole this wave of decentralized identity solution is through the various ERC, right? Ethereum request for comments. You have your digital identity aggregator, lightweight identity, ERC 720, ERC 725, of which I'm part of it. And then you have multiple smart contracts, in short, right, which will speak to each other, right? The claims, identity claims, and so on and so forth. Next slide, please. Okay, right. So what we have identified is that, of course, I think as what everyone would know, we have a scalability concern with Ethereum, with all the different rollouts, Constantine poll and all, right? Scalability is still something that everyone is grappling with, right? So there are many ways to achieve the same goals with different trade-offs, right? Correct. So this is a quick summary of some of these consensus algorithm, right? We have, but what captures our mind and the imagination is the Byzantine agreement, right? If you can see the Byzantine agreement, right? This protocol is a protocol in which users are privately and pseudonymly randomly selected to participate in committee to execute one step of protocol. And the privately selected committee members then broadcast a message which includes their proof of selection, followed by a consensus procedure. And we believe, even myself, my team and I, we are convinced that this is a very promising development. This Byzantine agreement could hold the key to the future of this decentralized tier for the identities to be stored, right? Okay, next slide, please. Okay. Okay, so you get the Algorand, right, overview, Byzantine agreement, right? So there are some challenges which this protocol seek to address. Number one is to avoid cyber attacks where someone impersonates an adversary, impersonates and creates meta identity to influence the agreement protocol. And secondly, must scale to millions of users. And third, being resilient to denial of service (DDoS) attacks, right? And continue to operate even if an adversary disconnects some of the users through network partition or whatsoever, right? So these techniques, right? And accordingly, in this white paper, you could read, have provided links over there. Very, very good mathematical rigor in these studies, right? Weighted users, right? Through the use of weighted users, Algorand assigns a weight to each user. And then this Byzantine agreement is designed to guarantee consensus as long as a weighted fraction, a constant greater than 2/3 of the users are honest. Second, consensus by committee. Byzantine agreement achieves scalability by choosing a committee, right? And it's completely random. And third, cryptographic sedition, right? To prevent an adversary from targeting committee members, the protocol selects committee members in a private and non-interactive way. Right. Next slide, please. Next slide. Okay, so this is the very high level. Of course, the mathematical formulas could be extracted in the white paper itself, in the academic papers itself, right? So using this VRF, right, verifiable random functions, one is able to ensure that a subset of users are selected, right, completely random, to ensure that this bunch of users can come to an agreement on validating the transaction, right? So next slide, please. Okay, so in summary, we believe, my team and myself, we believe that Byzantine agreement is the foundation, the protocol is the foundation layer for any decentralized platform, decentralized use case to happen at scale, right? In a secure and in a sufficiently decentralized manner. And of course, with all the developments in this space, we are keeping a keen eye, my team and myself in Singapore, we are keeping a keen eye on how this protocol, the development of this protocol, right, can help enable us, right, to be part of this global decentralized identity platform, right, to be part of this platform, right, in the future. All right, next slide, please. Okay, so this is some of the mathematical. In the previous session, there was a lot of mathematical formulas. So yeah, if anyone is keen to get down to the nitty-gritty of the formulas, they are easily accessible in the links provided. Right. Okay, next slide, please. Okay, DIF again. Very exciting. A lot of architecture being discussed and all. Right. Next slide. Okay, so this is my contact details. Feel free to hit me up, and we could discuss more on decentralized identity platforms and Byzantine agreement protocols. Questions, anyone? I think that's all.
Thank you, Nathan. Yep, feel free. So looking around, are there questions?
Anyone interested in decentralized identity, and
so there's one
works in the space. Yep.
Just a quick note in terms of our IPR policy. Maybe I'm David Mazeres from Stanford. We might need to note that Algorand is patented.
Yep.
Algorand hasn't been presented here, so it's sort of
okay. All right. Thank you very much, Nathan. So we hope to meet you in person in Singapore and later this year.
Sure.
Have a good day.
Thank you.
Bye. Do you have to? All right. So we're coming to our final presentation. And this is Brooke.
I'm shorter than everyone else.
Okay.
Hi, everyone. You may have seen me earlier in the week. I turned up at another research group. I'm here again, still spooking next generation internet project of the European Union. So I'm involved in one of the open call projects that I'm going to present today, but there's 4 other open calls that may be of more interest to you than the one I work on, but actually this is now slowly falling. So should do this. Okay, so this is a call by NLNet Labs or NLNet Foundation to have you work for the internet. So this is a project. In total, at the moment, there's about 20 million euros that's going to be on offer on various size grants, ranging from 5,000 euros through to 200,000 euros, depending on what you're working on. And so we hope that, well, you are here building the sort of next generation of the internet, and we want to focus your attention in some particular areas. So NLNet Foundation and Gartner got together. They were asked by the Commission to do this study to work out what will be the vision for the next generation of the internet, and actually to create an internet of human values. And so this study and this document is available online. You can go to ngi.eu/vision. They went through a consultation process. You can't really see this graphic. This is really for information. The readability is not there, but it created this big topic analysis of different areas. Now there's a pre-NGI process going on, which is what I'm talking about, and then there'll be further NGI projects happening in the not too distant future. So the consultation involved a larger ecosystem. I'm from GÉANT, which is the Association of Research Networks in Europe. It also involved the domain name registrars, RIPE-NCC, as many organizations as they could vacuum up that they thought would have an opinion on the development of the internet or a future internet in this space. In one of the topic areas that brought up, it was engineering trustworthiness. And actually the decentralized internet-wide identity mechanisms, which some have been presented here, are part of that space and an interest to be covered by this funding program. So, why did I come to the Decentralized Internet Infrastructure Research Group? Well, actually, the trust management and identity management components are of particular interest to me. We at GÉANT run an identity management service for research and education called EduGain. It's an interfederation that connects the identity federations that exist, often run by your local research networks. And there's some work on resource discovery that's presented in another open call. So some of these areas are interesting to me. Will the work that I've been doing for the past decade become extinct as a result of changes in this space, or how do we do the transition between those systems, or this coexistence of future identity infrastructure as well as what's in place at the moment? So this Internet of Human Values requires not just the underlying infrastructure, and some people believe that this infrastructure needs to be entirely replaced. Other people are building layers on top of existing internet infrastructure. And so both those thought patterns are being covered, right? So if you do have what some may regard as very crazy ideas, in the initial stages of NGI, they're all being explored, because even I guess the initial proposition of the internet was crazy at some point in time, right? It's just now so widely deployed that we just trust that those decisions weren't crazy at that point in time, because they've unfolded to be accepted. But these pillars that we want the future internet to be built on, touch some of your work, some of your research, and so there's a range of open calls that are happening right now. 4 in total. You can visit ngo.eu for more information. There's actually a very short deadline if you're interested in the search and discovery of NGI Zero Discovery or the privacy enhancing technology project of led by NLNet Foundation. That's an April 1st deadline. That's really, really soon. But for privacy enhancing technologies NGI Trust, which is the project that I'm in the consortia of, our deadlines are April 30. And the distributed ledger technology, ledger open call also ends April 30. So you still have some time. I got questions before. Some people said, what about the rest of the planet? How European focused is this? And there's actually 2 specific projects that are working on EU-US collaboration to make sure that an internet, our next generation internet obviously has to be for the planet, not just built only in Europe. So the focus is partnerships with European organizations and the associated countries, so they can directly get funding. And there's more, there's more information on the Commission website on who those exact countries are. These particular programs are targeted at EU-US collaboration. So it's best to work with a partner. You may interject if you want. No, you want to end? Okay. There's a specific program for EU-US, but best to form an Estonian e-business, look for partners in Europe to work with in order to be sure that you get funded. But actually, your proposal has to go to a panel at the Commission to decide on Europeanness, right? At the very end of the stage, we're not necessarily going to exclude your applications in the initial processing stage just because of where you're resident. And actually, it's actually where you're resident, not what your nationality is. So Europeans living and working for startups in the US could actually still be excluded from this program, unfortunately. This is showing the pipeline of future projects. We currently have 4 running real soon now: search and discovery, distributed data, and 2 privacy groups. And then there's 3 coming on board now. The deadline is real soon now for these to coordinate these open call actions. And so they'll be starting up later in the year. And then there'll be a further tranche of other open call projects that people can tap onto. So these are the ones being within Horizon 2020. So key characteristics, NLNet Foundation run the search and discovery and the privacy enhancing technologies. One of these open calls. They've got money between 5,000 and 50,000 euros available. You can apply as an individual. And they cycle every 2 months. So the fact that it closes on the 1st of April, it opens again for another 2-month window and closes. And this will be a rolling cycle until they run out of money. They have about 5.6 million euros to give out.
Now, at this point, I would like to ask the question, there's one additional thing that is missing in terms of key characteristics here that I was told by NLNet, which as a Swiss person hit me quite by surprise. As you might know, Switzerland is a bit more expensive than the Czech Republic. And they told me that the maximum salary you could pay to anybody in the organization, brut salary, under this grant was 65 euros per hour. I'm not sure too many people in Silicon Valley this is interested to do projects for 50,000 euros at a maximum salary of 65
I suggest
euros.
Can we clarify this offline? And this is just basically an information.
So then don't apply to NLNet Foundation, apply to
I was going to ask you,
project.
does this restriction apply to the other ones as well? That was my question.
No, we haven't worked out. I mean, it's a body of work. I know that NLNet are very good at handing out money with very low overheads and getting a lot of value out of that. But some of these things, well, okay, let's have, this is actually
This is out of scope for this.
So for this one, we also run a privacy enhancing technologies and a distributed data in the Ledger project. Ledger has up to 200,000 euros available. Some of their money is looking at the commercialization and support to turn your ideas into a business. So if you're ready, look at Ledger. You can actually do that now, and they all come with support, business incubator support, to actually get your ideas through a pipeline and actually running a business and hopefully making money out of your work in this space. Within our consortia, we have three projects where we give you varying amounts of money, like a viability project up to 100,000 euros. The next two options require co-financing, so we'll provide you 180 grand if you can find 90 grand for the next stage in the development of your project, and we'll give you 200 grand if you can also match it with 200 grand for the commercialization of your work. Contact me and ask questions.
Will do. Thank you very much, Brooke. This is good news for DINRG and probably some other IETF groups. Thanks for your announcement. Okay, we are at the end. So unless there's anything else, I think we can give you back a bit of your time. We need the blue sheets. Quick comment. So if you have any idea for, say, running or hosting a DINRG meeting outside the normal IETF schedule, please feel free to talk to us. For example, if you are organizing a conference or you just want to kind of meet in a smaller team, a smaller group, let us know. Thank you, and see you next time.
Make sure this is off because of what I'm about to say.
Yeah.